And we saw that you need to describe how the force is changing as your position X is changing. Well, we saw an example. I don't know what is the thing. You see, I write my own things here, and the English is not so good here.
You're on your own.
So we had a situation like this. So if you have a force like that is changing like this, it's a variable force, you'll have to integrate. Now you'll have to know how to determine f of x, depending on your context, whether it's a physics problem, whether it's a chemistry problem, whether it's an engineering problem. Last time we saw that in the case of a linear spring, the force is k times x. So that will be your function. It will be a linear function. That means the more you need to stress your spring and hold it, the greater the force you will need to apply. The k is the constant that determines what kind of spring you have. Yeah. So did we do this problem? The spring on a horizontal surface? No, we didn't do this one. So here's an example. We have a spring on the horizon.
Does it just turn autofocus on?
It just goes on by itself.
Oh, I'm gonna paste
Spring on the horizontal surface can be stretched and held 0.5 meters from its equilibrium position with a force of 45 newtons. What is that? That is telling us the spring constant. That is telling us what kind of spring you have. What kind of spring do you have? To stretch it 1 meter, you will need to apply 90 newtons. To stretch it 2 meters, you will need to apply 180 newtons. That is the kind of spring you have here. That is to say, not a shock absorbing spring. You will need much more force to stretch it 1 meter. So that is going to tell us K. That is to say, if, what is F? Oh, newtons. What is the newtons? It's a measurement of force. I don't know what they did. In the United States, they use a thing called pounds, which is sort of trash. Because pounds is the number of molecules in your body. Right. If your physics professor used pounds, ask he or she, why do you use such a thing? Okay. Really, if you want to use force, we don't want to we want to distinguish force from molecules. And so mass and weight are two different things. You can ask somebody what is their mass on Earth and what is their mass on Pluto. That is to say, how many molecules in your body, it's not going to change. But if you ask somebody what is your weight on Earth and what is your weight on Pluto, those are two different things. So when I say weight, I mean force. When I say mass, I mean molecules. So force, 45 newtons is, well, think of it as 45 cans of spinach, the measurement unit. How much cans of spinach do you need to stretch the spring? Half a meter, you need 45 cans of spinach. We just call it a newton, whatever. So, when the force is 45, you will need to stretch it half a meter. Well, the spring will stretch half a meter. That is to say, your spring constant is what? Your spring constant is 45 divided by 1/2, which is 90 newtons per meter. That is to say, to stretch the spring 1 meter, you will need to apply a force of 90 newtons. To stretch the spring half a meter, you will need to apply a force of 45 newtons. It's a linear spring. Linear x. So we know what is the spring. We have the spring is 90x. 90x. That is how the spring changes with your position. The force corresponding to how much you stretch it. So that is the function I'm going to use here for the next part. How much of work is done in compressing the spring 1.5 meters from its equilibrium position? So now you should always give yourself a reference. So you can say, well, this is 0. That's the equilibrium position. You can stretch it. So this would be positive x. And you can compress it. This would be negative x. Now what you want to do is, what do you want to do? How much of work is done in compressing the spring 1.5 meters from its equilibrium position? So that means I have to set up an integral. Keeping in mind that as you are compressing the spring, you are applying more force. I'm going to have the integral of x dx. From where to where?
0 to 1.5.
0 to 1.5.
0.5.
Huh?
0.5.
Well, we're going to go from its equilibrium position. What's the equilibrium position?
0.
So x equals 0. And we're going to compress it, meaning that means we are going to push it up. So up to where?
1.5.
Negative 1.5. Huh? Negative 1.5. Now you have to use your spring function, your spring force function. Yeah?
So when you push it become negative, then once you when you pull it, it's become positive.
Yes. That is if you're going to use this reference point here. If you're going to stretch, so positive, and if you're going to compress, and you're going to. So, you will integrate from 0 to negative 1.5 f of x, which is 90x dx. And you will do what now? You'll give it to your calculus one for now. That's the easy problem. You can check. You should get 101.25. What's the integral of 90x? 45x squared, evaluated at negative 1.5, evaluated at 0, and subtract. You get 101.25 units of work. Units of work are joules. Or Newton meters, force times distance. Newton times distance, meters, Newton meters. Oh, that's about 101.25 force times distance, Newton meters. Okay, I will put some spring problems up on the homework, next homework. Okay, let us continue with work problems. We're going to continue with this formula, but now we want to look at a force that is quite variable. I really want to look at a force that is quite variable.